So as usual, please open Jupyter Notebook. Let's make sure that we have annotation. Option language English, that should work. Okay, go ahead and open GitHub Intro Speech Understanding. And today is lecture 7. All right, now that you understand the basics of signal processing and you have the basics of Python and NumPy, now I want to start talking about speech, the main subject, obviously, of this series of lectures. So today I want to first of all talk about speech synthesis, which is the art and engineering of how to create sounds that sound like speech. Let me make sure that I'm sharing with audio. Let me see. Share sound. Yep. So speech is produced. Here's an image from Wikipedia showing the basics of how speech is produced. Speech is produced when your voice box here vibrates. Your voice box is a set of folds, a set of muscles, two muscles called the vocalis muscles that bump against one another, and they can be tightened in order to block your pharynx off so that you don't get food in your lungs. The main purpose of the voice box is to prevent food from going into your lungs. And sometime in mammalian evolution, perhaps dogs started to be able to force air through the vibrating vocal folds. So you can see here that this mirror is looking into the back of the lungs. And this is what it looks like when you look down into your throat via a mirror. When you look down, it looks something like this. And we can see a video. So I think you'll be able to hear this.
Here is a look at some normal young female vocal cords during a stroboscopic exam.
Are you able to hear that? Is it audible?
Yes.
Thank you. So this will be a stroboscopic exam, which means, first of all, we'll see it in real time, and it will vibrate so quickly that you can't see anything. And then they will use a strobe light in order to sample just once every period. So first of all, you can see that it's so quickly that you can't see everything. And now they're going to use a strobe light, which will flash once every 200th of a second, so that you can see the vocal folds vibrating much more slowly. So you can see how you can see that she brings her vocal folds together and then blows air through the vocal folds. And as the air blows through, the vocal folds flap like a cloth in the wind, like a flag in the wind. So you can see the two parts. The first part, we can see it at real time, and the second part is slowed down so that you can see how it's slowed down in much reduced speed. All right, so this is produced by using a mirror like this or a fiber scope. So we use normally a fiber optic scope, and then we use a strobe light in order to illuminate the vocal folds so that you can see one cycle every period. The vibrating flaps of tissue are called vocal folds. They used to be called vocal cords, but as you can see, they're not really cords. They're really folds or flaps of tissue. The hole in between is called the glottis. And the vocal folds seem to slow down. That's because the photographer is using a strobe light to slow down the apparent vibration. When the vocal folds open, they allow air into the vocal tract. So you can see the air comes through kind of like this. It speeds up as the vocal fold opens, and then the vocal fold slams shut. When the vocal fold slams shut, the air shuts off suddenly. And what that means is that the air pressure just above the glottis, as the air keeps moving, the air pressure suddenly drops. It becomes a very negative air pressure just above the glottis. And that negative air pressure spike is the main excitation for speech. Speech is primarily this negative air pressure spike echoing inside the vocal tract. The most important thing for you to know about pitch is the time between the glottal pulses. And this time is called the pitch period, T0. So you can see here that T0 is marked here. This time is T0. Right? So this is the time from one glottal pulse to the next. The time from here to here is T0. And this is the number of samples per pitch period, right? So if F0 is the number of pitch periods per second, Fs is the number of samples per second, then T0 is the number of samples per pitch period. So for example, if we have an 8,000 hertz sampling rate, and if we have a 110 hertz pitch, then the number of samples per pitch period is 73 samples per pitch period. Right, so we can generate a signal like this by simply taking Fs is the number of samples per second, F0 is the number of pitch periods per second, and then we can just create T0 is Fs over F0. Then we'll create an excitation signal which is all zeros, and then once every T0 seconds, we'll put in a -1. And that gives us a signal that looks like this. It's mostly zeros, but then once every 73 samples, we have a -1. You can see that this signal is a very crude approximation of this signal, right? This is what it really looks like, and this is the approximation that we use for speech synthesis. And it sounds like this. Right? So it does not yet sound very much like speech, but you can hear the buzz, which is the buzz of a male vocal folds. If we wanted to make it sound more like a female, we could change the F0 to something more like a female pitch. So a female talking pitch might be 250 hertz. And then we get something that has samples once every 40 samples or so. And if I play that, that sounds more like the pitch of a female speaker. Right? So a male speaker might be around 100 or 110, and a female speaker might be around 200 or 250. My pitch is a little bit higher than 100. My pitch is closer to 110. So let me run it at 110 in order to make it sound more like my voice. So that's very close to my normal pitch frequency. So that's the excitation. The excitation is all down here. It's in the vocal folds. And now let's talk about the rest of the vocal tract from your larynx to your lips. It looks like this. We have the vocal folds here, and then we have your lips or your nasal cavity here, and everything between these two is like a flute. It's like the resonance of a flute. You blow air into one side and you get vibration, and then it echoes from the lips to the larynx and back to the lips. So it's like this, the sound travels the lips and then echoes back to the larynx and then echoes back to the lips and then echoes back to the larynx. And this echoing back and forth creates a set of standing waves that look something like this. As the air blows in, there's very little air movement at the larynx because the larynx is so small. And there's also very little air movement at the lips because the lip aperture is so small. But there's a lot of air movement in the middle. Right around here in the middle, there's a lot of air movement back and forth. just kind of bouncing back and forth. We have almost closed, almost closed. In the middle, there's lots of air bouncing back and forth. And this is called a standing wave. It's also called a resonance. So the topic of this section is called resonance, right? So we have this excitation that looks like this, E of n, and E of n goes into a resonant filter, which is like a flute. E of n goes in here and it bounces back and forth. And that resonance can enhance certain frequencies, makes certain frequencies louder. We can imitate that with feedback. Notice that this feedback is because of echoes. We can imitate that with feedback like this, where we take the input signal, x of n, and we delay it and feedback, and delay it again and feed it back. And these two delayed feedback are enough to simulate a spring mass system, right? This is kind of like what you would see if you had a spring on a mass, right? You have it bouncing back and forth. And that bouncing back and forth is simulated quite well with just 2 unit delays, y of nt minus capital T and y of nt minus 2 capital T. And so we can take the output signal, which is equal to the input signal, plus a delayed copy of the output. Notice this is y and this is x. So here's x, this is the input. Here's y, this is the output. So we delay the output signal and then we delay it again. And those 2 feedback delays are enough to add resonance to the signal. We can use exactly these equations from this article in the 1970s. We can say that C is equal to minus e to the 2 pi bwt, and B is equal to 2 times e to the minus bw times t times the cosine of 2 pi f over fs, where f is the resonant frequency and bw is the resonant bandwidth. So I have the resonant bandwidth, I have the resonant frequency, and I have the sampling frequency. And I create the coefficients capital C and capital B in order to make the sound. And when I define this function resonator and then I apply it, let's say a 500 hertz resonant frequency and a 100 hertz bandwidth, then I take this signal, remember this is the excitation, and now I've added resonance to that signal. You can see that it's bouncing back and forth like those air particles inside the vocal tract. It's bouncing back and forth. And what that sounds like now is something like this. I think you can hear the difference between, here's the sound without resonance, and here's the sound with resonance. You can hear that already it sounds a bit more like speech because we've added this resonance like the air particles bouncing back and forth inside the vocal tract. In order to make it sound even more like speech, we need to add multiple resonances. So here's the first resonance. Here's the second resonance. At the second resonance, the air particles in the back part of the throat are going forward at the same time as those in the front part are going backward. So that's like if we go back up to our vocal tract here, it's like the air here is moving forward at the same time as the air here is moving backward. And so we have this, the second resonance kind of goes like this. And so here's the second resonance, here's the third resonance, here's the fourth resonance. And you can see that at each higher resonant frequency, we have a different standing wave pattern. Really, you can get pretty realistic vowels with just 2 formants, but in order to get even better quality, we're going to use all 4 of these first 4 resonances. There are an infinite number of resonances. We can get better and better quality by adding more resonances. But to start with, let's just use these first 4. So let's start with an ah vowel. For an ah vowel, a male speaker has resonant frequencies of about 700, 1200, 2500, and 3500. So let's just add those. We'll take the excitation and we'll generate a y1, and then we'll pass in y1 in order to generate y2, and then we'll pass in y2 in order to generate y3, and then we'll pass in Y3 in order to generate the speech. Notice that's just like going E of N goes into the first resonator, and then that goes into the second resonator, and then that goes into the third, and then that goes into the fourth. And these resonant frequencies are going to be 700, 1200, 2500, and 3500 hertz. And then finally, I'll plot the speech signal. And you see the speech signal, you can see the first resonance is really obvious, but you can also see that this is a little bit different. See, this one is very similar to this, but it's not as smooth. The non-smoothness here is because it also includes the higher resonant frequencies. And if we play this one now, it sounds much more like speech. Right now we're taking into account not just the first resonance, but also the second, third, and fourth resonances. And so we get something that sounds much more like a natural speech sound. So what I want to do with the rest of the lecture really is to create all 5 vowels, a, I, u, a, o. And the differences between them are mostly the resonant frequencies. So when you move your tongue around inside your vocal tract, you create different resonant frequencies. Let's see what that looks like. Let me see if I can expand this. Can you see this in large screen? You see the large image now? Okay, thanks.
Welcome to the Science Gallery of the Max Planck Society.
You can see that he moves his tongue tip to make a T, the tongue tip goes here. To make a W, the lips come together. To make a K for welcome, the tongue body moves here. But in between those consonants, the lip moves around in order to make different vowels. So the E, the E in welcome, the tongue is forward. And the in welcome, the tongue is further back. So if you look at that first word, welcome, you'll see the tongue move forward and then back for well and then come. So let's watch that again. Welcome.
To the
You see,
Science
it
Gallery
went forward for
of the
well and
Max
then
Planck
backward for come.
Society.
So the tongue moves around to make different vowels. And as it moves around, it changes those resonant frequencies. The first resonant frequency is F1. The second one is F2. And you can see that in this chart, oh, that one is no longer there. Okay, let me go back to this copy. In this chart, you can see that E is up here with a very low F1 frequency around 300 and a very high F2 frequency around 2200. So here we have E, A, O, and U. This particular chart is from Swedish, and so it also includes some of the Swedish vowels. There's E and U, A and O and Ö, A and A. So there's all of these different vowels in Swedish have slightly different formant frequencies, but the main ones that Japanese and most other languages have, Spanish, for example, are E, A, O, U. And really, we can simulate all of those. All of those have very slightly different frequencies and bandwidths for all of the formants, but the main differences are F1 and F2. Right? This is just showing F1, F2. We can keep F3 and F4 unchanged and make pretty good vowels. We can just say F3 is 2500, F4 is 3500. We can say the bandwidths are 1, 2, 3, and 400 hertz each. And so we can really just make F1 changes as a function of the vowel. A is 700, E is 350, U is 350, A is 450, O is 500. Those are just approximately these numbers. U is around 350, O is around 450, A is around 450, O is around 500, I guess. These are just me looking at this chart and approximating. F2, A is around 1200, E is around 2100, U is around 850. Let's see, that's about, oh, that's less than 850. That looks more like 800 or 750. Let's make it 800 then. A is around 1900. Yeah, that's around 1900. And O is around 950. Yeah, that's about right. 950 maybe. O is, oh, that's bark. This is hertz. Hertz down here. U is around let's see, this is 1,000, 800, 600, 400. So this is actually around 800, I guess. 15, 14, 13, 12, 11, 10. Oh no, this is 9, 8. So that is around 850. Let me make that 850. So now we'll create a dictionary that maps from the type of sound we want to make to the formant frequencies F2 and F1. Now that I have F1 and F2 as dictionaries, now I can go through and I can create, I'll take different phonemes, and those phonemes will be a, I, U, A, O. And for each of those phonemes, I'll look up the F1 of that phoneme and the F2 of that phoneme. And I'll create a speech signal, Y4. And I will concatenate that to an existing speech signal. So I'm going to take the speech signal and I'll concatenate speech with the new Y4, and then I'll concatenate 8,000 zeros in order to add silence in between the vowels. So this will produce a sequence of vowels. So here's the A, the E, the U, the A, and the O. Notice that all of them have the same pitch frequency, right? These are all set to imitate my voice. And so because they're imitating my voice, all of them have the same pitch frequency. And they all have different F1. Ah has a much higher F1. E has a very low F1. Actually, you can see that the F1 is this very gradual vibration here, but F2 is really jaggedy. So the second formant frequency looks louder for E. For U, both F1 and F2 are very low. So you can see that the F1 is a very low frequency. A is much more jagged, meaning that F2 is much more visible. O and U look kind of similar. E and A look kind of similar. And A is different from all of them. If we play it back, we get all 5 of those vowels. So there we have the key to making different vowels sound different. You can see they don't sound quite natural yet, but at least we've got them to be intelligible. So since I'm not translating in real time, that's actually the end of the main part of the lecture. Let me just talk about the homework. The homework will have again 3 functions. The homework for this week is really creating voiced excitation, and then creating resonances, and then synthesizing the vowel. So the voiced excitation, first of all, will take in a duration, an F0, and an Fs. And it should return an excitation, which is a sequence of impulses. So if we look at what that should look like in the notebook, we want to create the first 300 samples of a speech excitation signal. So it should be all zeros, except that there should be 1 pitch pulse every T0 samples. And let's see, that's very similar to something we've done before. Let me go up here. That's very similar to this, I think. So let me just copy this part. I think this is the part I need. Let me try copying that in here. I want this pass replaced with something that does something valid. Excitation is NP0's duration. That's about right. And then instead of just creating zeros, I want once every T0 samples to be a -1. But then I need to define what T0 is. I want T0 to be the integer part of Fs is in, let me see. T0 is in samples per period. And I want that to be, Fs is in samples per second divided by F0, which is in periods per second. So that's Fs over F0. All right, so we just have T0 as the integer part of Fs over F0, and then once every T0 samples, we put in a -1. Let's see if that works out. Let me go down to the homework part here. And I'll reload the homework and generate an excitation signal, and that looks about right. Let's make sure that we want that to be integer. -1 if n is an integer multiple of integer np round fs over f0. Oh, maybe I should do np.round here. There we go. I'll round it off in that way. Notice that the instructions here say to use np.round, and so I'll use np.round in order to round it off. All right. Homework part 2 is actually the same as the resonator. Given an excitation signal and a resonant frequency and bandwidth, and a sampling frequency, I want to produce the resonator output. So this is actually the same as this plot that we had. You remember we had this figure with all of these equations for what the A, B, and C should be. So I think this should be pretty much the same as this. Let me see. How do I copy and paste that? Let me delete the pass, return y. Okay, y is equal to np.zeros in the length of x, and then the coefficient c. So these are the coefficients from the CLAT paper, C, B, and A. And then I've already got an excitation y. And then I need to create the first 2 samples of y. And then after that, I create the rest of y. And then, so every sample of y of n is equal to a times x of n plus b times y of n minus 2 plus b times y of n minus 1 plus c times y of n minus 2. We need these first 2 samples to be initialized, and then after that we have a recursion where it generates each sample given the previous 2 samples. Let's go ahead and look back at the notebook. If I go down to the homework, here's the help file, and we should generate a signal that looks exactly like the resonance signal that we had previously in the notebook. And then finally, given the excitation and given the vowel, given the resonator, we should be able to synthesize a vowel. So the help on synthesize vowel says that F0 should be the pitch frequency, F1, 2, 3, 4 should be the first 4 resonant frequencies, BW 1, 2, 3, 4 should be the bandwidths, and FS should be the sampling frequency. And then it should return the speech. So if we go back to the homework, synthesize vowel, all right, it should start out as zeros, that's fine, but the first thing I want to do, I think I just want to call these others. So first I want to create a voiced excitation. And let's say E is equal to the voiced excitation, and the input should be I don't even need this speech signal. E is equal to the voiced excitation, starting with duration is given here, and F0 is given here, and Fs is given here, so all of those are given. All right, and now I need to run the resonator 4 times in a row. So let's say Y1 is equal to the resonator X with frequency F1 and BW1, and the input should be E. Then Y2 is the resonator applied to Y1 with frequency F2, bandwidth BW2, and sampling rate Fs. Y3 is the resonator with input Y2, frequency FB, bandwidth BW3, and sampling rate Fs. And then finally, the speech is just the resonator applied to the input Y3 with resonance frequency F4, bandwidth BW4, and sampling rate Fs. Now I've got F0, F1, 2, 3, 4, BW 1, 2, 3, 4, and Fs. I think I've taken into account all of those things. And then it returns the synthesized vowel. Let's try that in the notebook and see how that works out. So I'm running the homework 7 synthesize vowel. I'm running it with the F1 for each phoneme, the F2 for each phoneme, with F3 is 2500, F4 is 3500, and with the bandwidths 100, 200, 300, and 400. And I get an A, E, U, A, and O. Let me add something to listen to them. Um, oh, I have all of these different speeches, so I'll only be able to hear whichever one was last. That's all right. Let's go ahead and just grade it. So you can check your grade by running grade.py on your own machine, and you can see that this says it's at 100%. So once it's at 100%, then you should just be able to check it in with GitHub. Let's go ahead and synthesize it as well. Let's ipython.audio.display speech rate equals 8,000 samples per second. What did I do wrong? Oh, ipython.display.audio. Okay. So you can hear that the speech signal here is just the last one that I synthesized. Here I synthesized A, E, U, A, O, and the very last one that I synthesized was an O. And so when I play it back, I can hear just the last one, which was the O. All right, now that we've got everything working, now let's go to GitHub Desktop and check it in. So homework 7. I'll commit it and then push it to the origin. And then once you commit and push to origin, then you should be able to see it on your own GitHub page. So if I go to github.com, I'll leave this page. And go to my intro student speech understanding page, 2024 spring, lecture 7. You can see that homework7.py now has the excitation and the resonator and the synthesized vowel in the way that I just described. So go ahead and copy this URL and then go to Canvas, go to King LMS, homework 7. And then at this point, you should be able to just enter the URL for this week's homework. Are there questions? Okay, let's go ahead then and do the attendance. Sorry, because this is only in English, I guess we finished much more quickly, but please go ahead and check out the YouTube site as well if you would like to find a translation. Thank you. So everyone, please enter attendance using this number. Okay, thank you, everyone. 皆さん、お疲れ様でした。また来週お願いします。Thank you.